The Dalal hai. He's not coming today. Assalamu alaikum. So today we have a third day webinar. The webinar series that is optical forces on atoms. If you have any question, please write it in a chat box. For virtual participants, please, and for physical participants, you can write it and ask from us, sir, at the end of the lecture. So please, sir, thank you.
Well, Assalamu alaikum. Well, first, I'm very much thankful to Professor Dr. Iqbal Chaudhry Saab, Coordinator Journal Comstech, for his personal interest in the book and inviting me to present this 5-webinar series. So this is our third webinar in the 5-webinar series, and here we shall be talking about our next topics beyond our yesterday's discussion. So we have a small layout of our present talk that we are going to talk about atomic mirror, gravitational cavities, and then we shall be using these ultra-cool atoms in developing the newer techniques for microscopes. And then we shall be seeing that how we can develop quantum wires, circuits, and different networks for various different devices which are made in using ultra-cool atoms. Okay, yesterday we were talking about cooling phenomena. We were talking about how we can cool ultra-cool atoms and cool using various different techniques. And then we can have them in optical lattices. We were talking about that these optical lattices are prototype for our conventional materials, what we see in solid state physics normally. And then we can have various different experiments, what we do with conventional crystals here, but using atoms. Something which is very important is that here we have keeping in view the periodic optical lattices, we have ideal crystals which are completely periodic in the solid state scenario, which are very expensive. In order to appreciate a real crystal, we require to introduce the impurity effects as well. And without impurity effect, we cannot simulate quantum mechanically a real crystal using atoms. Now, those impurity effects can be embedded in our quantum mechanical artificial crystals, which are based on optical crystal, in numerous ways. And those techniques are available in my book as well, very well discussed. So and partly I will discuss those topics in my tomorrow's discussion. These atoms which are cold to very low, which are very to low temperatures in microkelvin and nanokelvin domain, have recently realized in space in microgravity. So this is the latest work, which is published in 2018, and and the advancement goes on in capturing atoms at very small scale, and to the limit that in our present day laboratory setups, we have the possibility to trap single atoms in a cavity or even single photon in a certain geometrical configuration. So this setup and these setups are very much common once we are very helpful once we talk about developing qubits using atoms or qubits using photon. So in developing quantum computers, we use these cold atoms very often. So and another thing which we were talking about yesterday was a scattering phenomena. We were saying that if there is a beam of atoms coming, interacting with a standing wave field, so this standing wave field would act like a diffraction grating, and the incident atom would be scattered accordingly. So the incident angle is an important quantity in this discussion, that if there is if the incident atoms are coming and perpendicular to the standing wave field, so this is named as Kapitsa-Dirac diffraction. So we shall see a symmetric diffraction effect, and that we see here. So the symmetry is seen in the probability distribution plots, what we see below at various different time of interactions of the atom and the field. Well, we can see this at a larger scale once we have a real diffraction grating made by the optical field for the incoming atoms. And this is a very simple experiment, but is done normally with classical fields and using material diffraction grating. So this is a college or school experiment where we see the image of diffraction grating on some screen once the light is passing through this. So this is a very useful phenomena, but now we are doing here using de Broglie waves. So the de Broglie wave, which are atoms coming, they're interacting with the diffraction grating made by the light optical field, and they're presenting image of the diffraction grating at some certain distance, which is normally named as uh, 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 Talbot distance. At half of the Talbot distance, we see again there are uh, uh, structures appearing and so on. So this mechanism, which is seen in optics very often, is useful in the development of very high resolution cameras, and they are also used in lithography to have some uh, structure on some material and so on. And the upper plot is showing the incident atoms at non-relativistic velocities, and they're presenting this behavior. The lower plot is telling us if the incident particle, the quantum particle, is coming with at a relativistic or near relativistic velocities, what happens? So this is a completely different behavior. So this is a famous Talbot effect. Coming back to uh, scattering of atoms, but now the incident atom is having some certain momentum along the cavity field, along the axis of the cavity field. So if this initial incident coming atom has some particular momentum along the cavity field, we say it as P naught, just naming it. And we shall see that after interaction with the cavity, which is having the optical field, the atom will be scattered. It will be scattering after a certain interaction time uh, to a direction P1, which is just to a direction P1. Okay, now we see that the incident atom, once it starts the interaction, is going to be deflected after a certain time of interaction. During this time of interaction, the atom is going to perform a transition from the incident momentum state P naught to the deflected momentum state P1. So this can be seen in the plot, which is shown here. So we see that if the incident atom was having a momentum P0, so after a certain time of deflection, which is pi up here, the atom is completely deflected to the diffraction to P1. So the probability of finding the atom with momentum P0 is 0 at this time pi, and then the probability of finding the atom in the next momentum state P2 is maximum to 1. So this is something which is presenting that the atom is completely deflected. In between, the atom is in a superposition. So it will be performing a transition, and at time pi by 2, there is equal probability, which is mentioning the atom is deflected and in not deflected state. If you compare with our first, if you remember our first webinar, where we were showing that this kind of behavior is also seen for the electron once it performs transition by absorbing light. So this is another way of observing the same phenomena, but now in the momentum state of atoms. So this gives us a good opportunity to develop quantum mechanical bits or qubits in the momentum state of atoms. So these are not, sometimes these are named as the flying qubits, and they are used for various different purposes in experiments. So this is again a topic of discussion in my book. You can see, and the interesting thing is that uh, this simple understanding is now going to help us in developing good experimental setups for atoms. So for example, using this deflection, which is Bragg deflection, we are in a position to develop interesting interferometers. And so if we let our atom pass through the optical field for a time of interaction pi by 2, we shall see it is having equal probability of being deflected and not deflected. And once it is, if we apply another field on the way, which is having uh, 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 and the atom is having interaction time now twice than earlier, so it will be deflected. The atom will be deflected, and they will meet again in the same plane. And then if we apply another beam of light, they will be combined together. And this is sometimes named as the Mach-Sender interferometer. This is very much useful in developing various different devices based on atoms, like gravitometer, like uh, uh, like uh, um, uh, these industrial sensors and so on and so forth. So there are various different applications. Now, we can take this discussion to the phase. So here we say it is an amplitude. Um, uh, so the incident wave is having an amplitude divide once the wave is going deflected and undeflected. But if we replace uh, the standing wave field or the diffraction grating, the optical diffraction grating, with the help of some mirror, so we can take the same discussion to build newer kind of interferometer, which are sometimes named as the phase interferometers. And here we shall require mirrors. We shall come back to the discussion of mirror after some time as well. So, so this is something which we shall be seeing again. There's a very good discussion of atomic interferometers in my book, so we can have in good detail that discussion being in the book. So now we have components. So what we gained up here. So this is something which is very useful, that by developing beam splitter, by developing mirrors, by deflecting diffraction ratings, we are basically making the components to control our atomic dynamics. Now, this atomic dynamics is now useful in developing numerous useful devices, which is the goal, basically. We want to develop devices based on atomic dynamics and atoms, multiple atoms. So this is giving us basic components to build all those devices. So if we move onward and we want to see which kind of components, devices, which kind of devices can be made using these components, so we come across various different options, various different devices, which we shall be discussing. And one of them is in the developing the position sensor, or sometimes we name as microscopes. But since we want to talk about atoms, we want to observe atoms. We want to have our resolution up to the size of atoms. We shall be requiring this microscopes to see, to resolve at the nanometer scale. It's very, very small. So we have to increase the resolution of our existing microscopes or to develop completely new microscopes, which are where we are using atoms again to see atoms. So which kind of microscopes we have in mind? So if we just talk about uh, position sensors or microscopes, so the question is how we can see in a sample surface or a sample object under discussion, or how we can sense or image or anything out of these three options. That would be meaning that we are seeing an object, or we are able to work with an object. Either we see it, we image it, or either we sense it, just like our fingers. It can sense something, what kind of object it is. So these three targets are obtained by developing three different kind of microscopes. For example, electron microscope, optical microscopes, and scanning probe microscope. So electron microscope is developing image of a surface, which is under study. Optical microscope is giving us opportunity to see directly an object which we want to study. And scanning probe microscopes are there to sense. So they are our fingers at the nanometer scale with which we can really sense anything we want to sense. So in electron microscope, we send a beam of electrons over a surface, over a sample, and image is obtained on a screen down there. So this is a very first suggestion of microscope which was suggested other than the optical microscopes. So it was in 1933. It was Siemens project, and they developed it. But the problem up here is that once you expose your surface or any living object with some electron beam, so you really charge it. You provide electrons over this. It may even, if it is a living object, it may be killed after that. The electron beam is passing through this. Then we have this optical microscope which see an object in image, a sample directly. So, but the problem is that these optical microscopes have a limit of resolution, which is equal to the wavelength of the optical light. So if optical light is having a wavelength of a micrometer, 10,000 of angstrom, so we cannot see below that. So this is giving a natural limitation in using optical microscopes. There are some good approaches to increase the resolution of these microscopes, um, uh, and again using quantum mechanical methods. I shall explain it at some later stage. So using quantum mechanical methods, how we can improve the resolution of these optical microscopes, because it is always very nice that we want to really see something down there. That is fun. But the cost is that once you use methods to improve the resolution in optical microscopes, you heat up the sample. So that is another, and if it is a living object, it may be killed. So, or if it is non-living object, you may change the property of resistivity or something like that. So again, there is a cost. So then we have a whole bunch of scanning probe microscopes. Now, the scanning probe microscopes are using different approaches to sense a surface. How we can really sense. So it is just like our fingers. We probe over a surface and see how it appears. So we want to have an understanding what this object can be. So we have a sample surface up here, and so one of the first one is a scanning tunneling microscope. The other is atomic force microscopes, and then there is recurrence tracking microscope in this discussion. So we have the scanning tunneling microscope based on the tunneling phenomena. So it's a macroscopic tunneling between a needle which is having the tip of atomic size, and then once we move this tip over a surface which is again made up of atoms, we can see wherever the tunneling current is less or more, give a feeling of the surface structures. down there. Okay, now the macroscopic tunneling effect is given Nobel Prize this year. So this is an interesting connection with this. And then using this technique, we can very accurately, at the scale of nanometer, we can see the surface structures. So it's a very useful technique. But there are some limitations, problems. The problem is that if there is some impurity atom, which is having different conduction property, will either be seen drastically bigger or will not be seen if it can't tunnel an electron. Other problem is that if we have uh, 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 if the surface is non-conducting on its own, it is a not non-conducting surface, so the tunneling current cannot be used at all because electron would not tunnel to a surface which is non-conducting. So so again we have a limitation of the samples which can be scanned using this scanning tunneling microscope. And then for every kind of material, we have a different kind of cantilever, which is now going to be another problem. So these are some limitations. To avoid these limitations, the inventor of STM came up with another idea of atomic force microscope. An atomic force microscope is using, so it is scanning tunneling. So atomic force microscope. So atomic force microscope is using a tip, but on the upper side of the tip, we have a reflector. It reflects a laser light. And any change in the angle of reflection will be seen as its appearance of an object underneath the cantilever. So this gives a feeling how much the surface change is happening because the change of angle will be seen accordingly. So this is an atomic force microscope, but the limitation is that this is a classical device. This is not a quantum mechanical device. So it is having again the limitation of the wavelength, because the reflected light, the wavelength of the reflected light becomes the upper limit. We cannot have a better resolution beyond the wavelength of the light. So this becomes a limit. So this is something which is interesting. So we need a quantum mechanical device, and that quantum mechanical device comes in the form of a recurrence tracking microscope. So what we have here, we have the same cantilever which was using in STM and AFM, but now we have a reflector which is not reflecting the laser light, but it is reflecting the atomic de Broglie wave. So we are using atoms, the ultra-cool atoms, in the form of de Broglie wave and reflect them. And once the de Broglie wave is reflecting back, it interferes because a wave. It interferes with itself. So this is becoming the principle of the recurrence tracking microscope. So here, no need to worry about the theoretical details, but this last equation is very known to us because we were using this yesterday, and we were telling that the atoms which are coming under gravity and meeting the surface, meeting the optical surface, will observe an effective Hamiltonian of this kind. This first term is talking about the momentum they have because they're moving atoms, the kinetic energy term. Second term is the potential energy because it is based on the position. This U of R, you remember, this is the spatial profile of the field. And in this case, the spatial profile of the field is exponentially decaying. So without worrying about that, we notice that this, okay, gravity is also taken care here. So this force is, this force is going to be, this optical force is going to be calculated by using this simple relationship as minus del V. And this gives us a very simple relation. This delta is detuning. If delta is positive, we see the force is repulsive. If delta is negative, we see the force is attractive. So for our purpose, we want to have a repulsive force because we want to repel the coming de Broglie wave, that is atoms. So this de Broglie wave is coming, meeting this optical surface, and is reflecting back. So this is something this is making us to require that we require delta to be positive. Delta is simply the detuning between the field frequency and the transition frequency, or any transition frequency related to the atom. So field frequency is really big in this sense. So this determines the force which is being provided by an exponentially decaying field, because on the surface of the dielectric, the field in the vertical direction is going to drop exponentially. So this decay of the field exponentially is going to present the U uh, function as exponential of minus kz. Z is a vertical direction. So this makes the force to be an exponentially decaying force. So the atom is coming towards the surface and going to see an increasing repulsive force. So it makes a mirror for the atom. So it's very simple. So this is something which is going to add one more component to our toolbox, which we are preparing to control the dynamics of atoms, ultra-cold atoms. So this makes it interesting to make the useful cavities for the atoms. So we have on one side the mirror, which is the atomic mirror. It reflects the incident de Broglie wave. And then we have gravity on the other side. So atom goes into gravity, exhausts its kinetic energy. Once the kinetic energy is zero, it is a turning point. It comes back again to the mirror and again bounces. So this is something we can have various different um, bounces of the atoms. So in the real experiments, people have seen thousands of bounces of the atoms. So this is very useful. So that simply conveys that this kind of setups are very stable setups. We can control them, we can use them very comfortably. So now we have this thing in our control. So atom is going to see a bounded dynamics between the gravitational potential and this exponential decaying potential. So it is a closed oscillator kind of movement. Okay. Another thing which you can notice very carefully, that this potential is very much similar to that of the Coulomb potential. Because here, here we again have, if we calculate if we calculate the eigenstate and eigenenergies, I'm going little in the quantum mechanical discussion. We may need it or we may not need it, but just to say, if it is useful, keep it with you. If not, then don't worry about that. So if we go in the quantum mechanical calculations, so we find eigenstate and eigenfunctions. And thing which is very useful, that this appearance of the potential is very much similar to what we know as the Coulomb potential. And one difference is that in Coulomb potential we have a continuum, but here we don't have continuum. So any higher we go in an energy scale, we should still find some energy levels. It's very interesting. So this is something which is useful. So if we let this atom move in this cavity, which is gravitational cavity, we shall see that this is going to display very interesting behavior. It comes from a certain height, meet the surface, reflecting surface or reflecting mirror. This is the wall, this is the reflecting surface, and comes back, it bounces back. Since it is a wave, it performs interference with itself and is now broadened, just like a wave. And then it goes again to the mirror and broaden again further. So you can compare it with something like what happens in a teacup. If you just drop a sugar cube in the teacup, so you see ripples. The ripple goes to the wall, they come back, they're lesser, and they go again to the wall and come back, they're even lesser. And after some reflections, you see there is nothing. Fine. Quantum mechanics does not allow this, that there is nothing. Quantum mechanical dynamics will permit that the way it is vanishing, very similar way it reappears. It's very strange quantum mechanical phenomena, which is named as quantum revival. So that quantum revival is seen in this atomic movement again. So we see this one is telling the maximum probability of finding the particle. So you can say it is our sugar cube, which we dropped in the teacup. So this is maximum probability 1. And as the time evolved, this is the time axis. So we see the wave is now disappearing. But now this disappearance is not permanent, which we see in our classical systems. It is disappearing. The energy of the fall, energy associated to the cube has gone to the T itself. So it is a change in the shape. But now here we see that the probability is dropping down to very low value, but then it reappears at some certain time. So here we are seeing this peak is approaching 1. So that means that our initial wave packet is almost reappearing at this particular time. So that is, I was saying that the movie is being played reverse in time after the drop has happened. So this is something which is named as revival phenomena. So in the dynamics of these atoms, we have to wait till the atom reappears. And that is something which we want to record. That is important. And this time of revival is directly proportional to the height of the atoms, Z naught. If the Z naught was large, the time will be large. If Z naught is less, the time will be less. This is making the principle of this recurrence tracking microscope. Because if we notice that the cantilever is going down, because surface structure, there is no surface structure, so the cantilever will drop down. This will take this atomic mirror going down, and the distance between the atom and the atomic mirror is increasing. That will be presenting this quantum revival at a longer time. But if we see there are structures on the surface, and this needle is going up following the surface structure, so this will reduce the distance between the atom and the atomic mirror. So the reduced distance between the atom and atomic mirror will make this revival at a lesser time. So change in the revival time will give us an understanding about surface structure there or not. So this is a very simple approach. So this is making the discussion. So here we can see that if we have one height of the atom above the mirror, so we see one kind of revival. But if height is changed, so it changes the revival time. So that would be the scene recorded in our calculations. So this change is now going to help us to understand about the surface structure, it's there or not. Now, we have developed this recurrence tracking microscope in many ways. For example, we have used optical atomic mirror or atomic mirror made by optical field. At the same time, we can make atomic mirror using magnetic surface. So that is again something which is we have shown in our book. And then many configurations. We can use one mirror and then we can use another mirror and make a confinement, a cavity. And okay. Um, Okay. Well, okay, so we were talking about the atomic mirror, which is based on the exponentially decaying field. Now, this simple effect can be realized in various ways, and that helps us to make some configurations which are unique in their own applications. For example, if we have a optical fiber, which is made of dielectric material, and pass an optical field as as per normal. So we find the field outside the optical fiber is exponentially decaying. Fine. So this exponentially decaying field is the field which we were using earlier on a flat dielectric surface as atomic mirror. Here we shall also be able. We can also use this in the form of in the form of a cavity and trying to hold our atoms around them. If we keep in mind the atoms which are placed near this optical fiber may follow a circular dynamics around the optical fiber. If we have some coal atoms, we let the coal atoms come closer to this optical fiber. They will be following a rotational dynamics around the optical fiber, and they will be having a centrifugal force. So now, if this exponentially decaying field is providing an attractive force, and there is a centrifugal force for the atom which is pulling this away, so there can be a point where the two forces are balanced, one inward, the other is outward, and that will be the balance point or minimum point. Fine. So the atom can be balanced, can stop there. So it can just keep rotating around this optical fiber uh, in a stable form. It may stay there. So the atom is going to see a potential which is of this form. This is close to the surface. We see an exponentially decaying field. This is an optical field. And as we go away from the surface, there is centrifugal force. So if we move, if we come closer to the surface, if the atom come closer to the surface, it will see a dominant optical field. If it is away from the surface, it will be seeing a dominant centrifugal potential. So this is something which is going to make this complete. Now, something is very interesting here that different from the previous cavity or different from the previous potential, here the potential is very much mimicking the atomic or hydrogen atom potential or atomic potential seen by the electron inside the atom. Again, it's little mathematical discussion that if we solve this potential and calculate the eigenstate and eigenenergies, we should see they follow very much similar behavior as an electron sees the energy levels in an atom. So here we also have a continuum as well. That simply means that if the atom has high energy, it may even escape from this configuration. It may run away from the optical fibers potential as well. And that we see in the electron as well. In the case of an atom as well. If you provide enough energy to the electron, it may be free from the electronic dynamics. So this comparison gives us a beautiful analog as well, that now this atom is going to appear in an orbit around the optical fiber, because it is confined radially. So this orbit is going to be only along the axis of the fiber in the radial direction. At a distance r, it will be making this circle. And another atom, which will be following stable dynamics in this system, would be at a higher energy. So we shall be seeing the orbit behavior for the cold atoms very much the same as an electron sees in an atom, sure. So this is a very good comparison, a prototype of an atom. So that's why we may say this is an artificial atom, because here we have the same energy spectrum, very much the same energy spectrum, and a continuum with all similar properties, but at a very large scale, because this is this optical fiber is composed of dielectric material, and it has billions of atoms in there. And we are talking in each atom, electron is observing this potential, what we see here. So it is realizing the same atomic behavior which is seen by an electron at a very different scale. So we can say it is an artificial atom. So now this configuration can also be used to develop something like a waveguide, because what we notice that the confinement is in the radial direction. But along the axis of the fiber, the field may push the atoms to propagate, to move. And this will be helping the atoms to come along the optical fiber in a coherent way. So this is a waveguide. So the optical fiber guides the de Broglie waves to move in a direction where we want to take it. So this is another interesting manifestation. So this discussion you can also see in my book. And so now we come to another topic. So again, this is a use of our exponentially decaying field in making some newer configurations which are helpful to control atomic dynamics. Now, if you remember STM, you remember AFM, you remember RTM, so you found they have one common thing, and that is cantilever. Cantilever can be used in a reverse mode as well. And that reverse mode means that because I mentioned that the cantilever has a tip of the size of an atom. If we make this cantilever charged, it can collect atoms, and then it can drop atoms wherever we want to place it. So this can act like a atomic crane itself. So it is STM, AFM, or RTM. We are talking about the cantilever. So if we provide a charge on the cantilever, so it can attract the atoms, and then these can be placed in any configuration we want to make. So this is something which is sometimes named as the billiards, atomic billiard. So here we have all iron atoms, and there is one iron atom sitting inside. So purpose of this configuration was, once it was made, to see how the inside atoms will behave. Because now there is a wall outside of iron atoms. If you place one iron atom inside that, how it will behave? Because our understanding is it's a wave. And that is exactly happening right here. Because we see that this atom is appearing like ripple, and it moves symmetrically and goes to the walls and then reflect back. Very interestingly, the way this wall is made, it is acting like diffraction grating. Somewhere the atom is having a hum is there, and some place it is very less probability. So then the diffraction grating effect, which we were talking earlier, are also seen here, and that is the interference. So outside this, on the other side of this wall, we see the interference pattern sitting there. So this is something which is only using atoms. So this way, this is again coming into the lithography as well. You can have very smart pens which can really use atom by atom and write whatever you want to write. And for sure, only those people can read that writing who have that resolution of single atom. And that is requiring high resolution microscope, which we are discussing right here, like STM, AFM, or RTM. So this is something which we're talking. And then using the same single atoms, we can even make wires. So this is a wire made of single atoms. This is sometimes named as one-dimensional wire, because nothing can be thinner than this wire, this having a thickness of an atom. So there cannot be anything thinner than this. So this is named as one-dimensional wire. It is also used in our very expensive electronic circuitries, because now we make these wires and let atoms move on them. Electrons move on them, because electron will jump from one atom to the other atom and move in this way. So we are in a position to talk about single electron current, right, which is moving on this in this configuration. Okay, so so here we are. So here I mentioned that in our next talk, which is tomorrow, we shall be talking about systems in higher dimensions. And we shall be able to talk about phenomena like quantum recurrences, which is beyond, which is ahead of quantum revivals. Then I will be presenting time crystals, which is very beautiful phenomena, how we can see crystal in time only, localization, and then we shall have some discussion of ultra-cool atoms in optoelectronic systems and applications in switches, transducers, single atom or photon transistors, and so on. So this will be our topic of discussion tomorrow. So any questions are welcome. Thank you.
Okay, if anybody have a question from physical participants, so feel free to ask question from sir. Okay.
Sir, can you mention the applications of the flying qubits? Applications of flying qubits. Are they used in quantum computing also or not?
Okay, do you want to speak? Okay.
Okay, so your question is that how we can use flying qubits. Okay, you see, we can use these flying qubits in communication, data communication, cryptography, and various applications. So here we have, once we talk flying qubits made by atoms, we can have a very good control on the velocity of the flying qubits, because now we are talking about material waves or matter waves. We can control their wavelength and velocity. So so we can have communication in our hand. We can also make these flying qubits using optical fields in polarization, using polarization of the optical field. So, but the limitation or difference would be there that they move with the velocity of light. So we have to have really big circuitries, maybe where we use flying qubits in our communication using optical field, and we use without any worry. We have such big experiments. But if you have in a small range setup, and you want to have a good control of the speed of your flying qubit, you have to use atoms.
You have also mentioned about the one-dimensional wires of the atoms. So this, I guess, this phenomenon is on very micro scale. How can we handle it for in Pakistan? Are they using in any type of making the circuits or sensors, microchips? Is there any laboratory use this type of techniques?
Well, not to my knowledge. I don't think so. In Pakistan, there is any experimental development happening. I don't think so. But it's very easy to be done. Okay, what you want to do, if you want to talk about single electron current, and you want to take it from one place to the other place, as in the one-dimensional wires, you can do it in different ways as well. For example, I was just showing, can you come back to my slide? I want to come back to my slides. So, for example, I was showing you, an experimental arrangement where you can use optical fibers, and then optical fiber is confining basically. Optical fiber is confining atoms in the radial direction, and then this optical fiber has a tendency to take atoms in along the axis of the fiber. Now, if you simply place one, if you replace atom by ions, and you have single ion stored up here, so then this electron, it is having all the same property as that of an electron, because it's a negatively charged, and it is having the spin, and only difference, it is having a big mass. And then you can take it from this point to another point or any direction, from upper to the lower direction. It's move. So you have a single electron current now again. It moves, electron moves. So you can realize that single electron current on a large scale in a controllable fashion. So now you can make anything.
Anybody else have a question? Okay, let me ask a question from a virtual participant. The question that is asked by Wajiha Masood, and she's asking what happens to the optical forces if an atom is a superposition of ground and excited states.
What happens to the optical force if the atom is in a superposition of ground and excited state? Well, if you have if you want to have the atom in the ground and excited state and then see how it interacts with the optical field, so you would be working the non-dispersive domain. That means you would be using resonance scenario. So in the resonance scenario, what we were seeing, the force would not be applied on the field, or it will be very small. And then it would be cancelled because of emission once the emission is happening. So this will be this will be a scenario. So if you want to have if you want to see an appreciable force acting on the atom, we have to think of we have to take the discussion to the non-dispersive, to the dispersive regime, where we have large tuning between the field frequency and the atomic transition frequency. So population, if you have in mind still the ground and the excited state population, which may be there because of the initial arrangement, so it will not change in the dispersive regime. And that we were also discussing in our first webinar, that once the interaction takes place in the dispersive regime, so the probability does not change, it remains the same. So that would be happening.
Okay. Okay, thank you, sir. So next question. Okay. I think sir, today we have one question that is by the Wajiha Masood, and that is like, let me check it if somebody. Oh, she's saying okay, thank you, sir. Or okay. Yeah, sure. Yeah, indeed.
Okay, if you have any question, you're very much welcome to ask, and I'm there to answer. I'll try my best to answer your questions. At the same time, anybody who is interested to work in these new areas, new applications, new technologies, named as quantum technologies, you're very much welcome to join our group. Thank you.
Okay, I think, sir, today our time is completed. So the Momna, she's saying, I want to join to work with you. She's saying this to you. And okay, dear Momna, sir, read your message and we will let you know. So, okay, thank you so much. So we have tomorrow we have a fourth session, fourth webinar, fourth lecture of the webinar. So please join us and thank you. Okay, thank you, sir. Thank you. And please join us all for a tea break.